many signals you have into
Yeah.
Oh, yeah, that's why that should be about download a new PowerPoint.
I think so.
I'm always thinking this. Okay.
It changes the software update, everything like this. Well, you know, at least I got the PowerPoint slide because unfortunately I can't do it. Oh.
Making the old ones blue.
Oh, you like it?
I like it because I don't know. Oh, no. Oh, yeah. That one's cool. I meant the one.
I suppose everybody is still in vacation, winter vacation. Anyway, it's my great pleasure to introduce a friend of mine, long time friend of mine. I have to tell you really how I met him. A long time ago we came up with vitrectomy and intraocular fiber optic illumination. And one of the big problems was the danger of phototoxicity. So at that time, it was 1978, I was moving back and forth between Miami and Durham, where Duke University Eye Center was established, and Robert McEnroe was a German. And he had this guy called Myron Woolbach. And Myron was the someone of photo sensitivity, or maybe photo killing, right? And he only spoke about one other person, and this is Leo. And this is how I really learned about his work and all the good things he did for us. So David is a bachelor's degree in physics from Virginia Polytechnical Institute, master in physics and radiological health from Emory, PhD in physics and medical physics from the University of London Institute of Ophthalmology, which in Europe is known as the Institute for years. Now it's us. Correct? Yeah? And then David spent 42 years at the US Army Medical Department. He was program manager of laser optical radiation program until he retired, which was just a few days ago, right? He has been very active in the establishment of health and safety standards for the protection of the eye and skin from sunlight, lasers, ultraviolet, and high-intensity optical sources. His studies in vision, thermal, and photochemical effect upon ocular tissue aided the development of laser application in medicine and surgery. Actually, every single time a new laser came out, David was required to not only test it, but consulted with either the manufacturer or the laboratory that created these lasers. And that includes lasers used for photodynamic therapy, in which we are involved. He's also best known for two books, two Bibles, if I may say, Safety with Laser and Other Optical Sources, that he wrote with Myron Woolbach, and Medical Lasers and their Safe Use with another friend of mine, Professor Stefan Schrotter, who is at Columbia in New York. He wrote over 200 peer-reviewed scientific papers, all of course related to that field. He's on the editorial board of photochemistry and photobiology. That's going to be very useful. Photodynamic therapy, biology. laser and light in ophthalmology, annals of ophthalmology in glaucoma. Is member, advisor and chairman of committees active in the establishment of optical safety standard, which includes ISO and all of these other things. I don't even know what they stand for. I know they're important and we have to abide by them. He received the Wilkening Award and Charlotte Award from the Laser Institute of America and the award for distinguished scientific achievement from the Health Physics Society in 2001. You must also add he was a Fulbright scholar in 1977. He's co-chair of the International Symposium on Retinal Toxicity that was held in Paris in 2013. I bet you want to go back there. And currently is faculty at Drexel in Philadelphia as well as Johns Hopkins. And he's a member at large of BPI's Ophthalmic Biophysics Center. He's also serves as independent consultant. So whenever we need you, we should be right. Maybe so yours. Thank you
Thank you very much. I hope I still have some time for my talk. I'm delighted to have the chance to come down whenever it's possible. I always learn a lot when I'm interacting with the laboratory here. So today I was asked to say something about phototoxicity and also ophthalmic instrument safety. And so I just to put the definition up here and point out that in terms of human health, phototoxicity is of particular importance when we're talking about acute effects like sunburn and welder's flash or snow blindness, photokeratitis and erythema. And then chronic exposures, it's well understood that well over 90% of skin cancers originate from excessive sunlight, ultraviolet exposure. Cataracts, which we'll mention in a few minutes, pterygium, and some unusual keratopathies that are in very high sun environments. And finally, there's questions about effects on the retina. Certainly, everybody recognizes the acute effect of photomaculopathy or photoretinitis when somebody stares at the solar eclipse. And we'll probably have a lot of cases this August because we're having a major solar eclipse across the U.S. But there's been a lot of basic scientists who have speculated that excessive light exposure plays a role in age-related macular degeneration. But that seems to be very controversial, particularly when you look at the epidemiological studies that have attempted to look at that relation. So the first thing we need to point out is, in talking about any type of phototoxic effect, is that we need to think of light as photons, as little corpuscles of energy, as Sir Isaac Newton had speculated, and that each photon has a given energy that depends on wavelength. And as you move up the spectrum towards higher energies, you move from the visible, from the red to the green to the blue, violet, and on ultraviolet. So the reason we have a lot more phototoxicity with short wavelength light and ultraviolet is that you have higher energy photons. The other key thing to remember is that in photochemical reactions, one photon interacts with one molecule, so either causing photoisomerization or bond or what have you. So this band of interest of phototoxicology is really roughly the ultraviolet, and short wavelength visible. That's where we have most of these types of effects. And Robert W. Young, who was at UCLA and was well known for discovering photo repair or repair in photoreceptors and photoreceptor renewal, wrote a book some years ago on age-related cataract, where he was arguing that most of the effect was from ultraviolet, and he argued that there are many different molecules, biologically important molecules, not just DNA and other proteins, that can be altered by short wavelength light, and therefore speculated that there were a lot of potential effects. So when we're talking about a photobiological effect, the key thing that all photobiologists look for is an action spectrum. And an action spectrum is simply the relative response for this given reaction as a function of wavelength. So for example, you have ultraviolet germicidal action or ultraviolet photokeratitis follows an action spectrum that looks somewhat like this, that actually follows pretty closely the damage of DNA. And then in the physical, we have an action spectrum, the so-called blue light hazard action spectrum, which is for retinal phototoxicity, eclipse blindness, and so on. And then, of course, vision itself is a photochemical reaction. One photon interacts with one rhodopsin molecule or other visual pigment molecule. And we have the action spectrum for human vision, for phototoxic vision. And normally, it's something important to point out is that there's always a long wavelength cutoff where you go to longer wavelengths, there just isn't enough energy to interact with the molecule. So let's look at some eye diseases that seem to have some relationship to ultraviolets in sunlight. Cataract has long been suggested is related to ultraviolet exposure. First of all, because just like skin cancer, it was noticed that there was a much higher incidence in the tropics, or wherever you had a lot of sunlight, compared to northern climates, like northern Europe. And then in some very special environments, like Labrador and so forth, where you have a lot of ice fishing and so forth, you sometimes see degeneration of the cornea. And this goes by different names, such as spheroidal degeneration and stuff like that. But you notice that it's in the lower hemisphere, which is certainly, again, suggesting that the UV is coming from below. And then we have pterygium, which we have two photographs of two Australians here, one with very dark skin and one with very light skin of European origin. And you notice, though, that they're both suffering from pterygium. And an ophthalmologist in Australia pointed out that most of these tend to start in the nasal quadrant. We'll say something more about that. The next thing we need to do is, okay, if UV is related to any of these chronic eye diseases, how do we get exposed and what's hazardous? And what a lot of people don't realize is how enormously different this UV exposure is when the sun is lower in the sky, when we start to see it, and when it's high in the sky. If you asked a bunch of little elementary grade school children to draw a picture with some color crayons of some outdoor scene, you know, some would have a house, some would have a horse, a car, a person standing there, and you might have blue sky and some clouds. But what color would they color the sun? Yellow, I think we would all say. And why would a child color that sun yellow? It's because when the sun is overhead, it's white. It's a very relatively flat spectrum, equal amount of blue, green, and so forth. But yellow is the origin when blue has been filtered out. So the blue sky is filtering out by Rayleigh spectrum all of the direct short wavelength ultraviolet and blue rays. In fact, most of your UV exposure comes from the sky, not from the direct sun. If you could see down in the UV, it would just look like a big cloudy haze. And at 300 nanometers, which is the peak for many of these damaging effects in cell cultures, in skin cancer research, and so forth, within just plus or minus 3 hours of solar noon, that would be 10 o'clock and 4 o'clock in summertime, and 3 o'clock, 9 o'clock, and 3 o'clock at this time of year, the sunlight is reduced somewhat, maybe 30%, but the ultraviolet, right around 300 nanometers, is reduced by about a factor of 10. So that means somebody with very fair skin, such as I, who can easily get a sunburn, can go out and, say, play golf from 7 a.m. to 10 a.m. and no chance of getting a sunburn. But if I go out and play at solar noon, in 20 minutes I'll get a sunburn. So that's why dermatologists tell their sun-sensitive patients, be sure to stay out of the sun between those hours around noontime. So how does that affect ocular exposure? When you think about it, we're not going to get a lot of direct sunlight when the sun is straight overhead. So I've spent a lot of time over the years measuring the UV in different parts of the sky and what the eye is exposed to. And we and some Asian labs have measured UV reaching the eye as detected by mannequins and so forth. And sometimes put some sunglasses over these mannequins to see how protective or not protective they might be. But those types of measurements still have a problem in that they don't take into account behavior and how people tend to avoid looking in the direction of the sun and so forth. But what these studies all show is the greatest illuminance on the eye occurs when the sun is lower in the sky, not when it's above. There have been some epidemiological studies of cataract and other ocular diseases as a function of latitude, and probably the most prominent of these were done by the ophthalmologist Ko Sasaki from Kanazawa Medical University in Japan. He died a couple of years ago. But he and his team used shine-through illumination, took images of the anterior segment of the eye in a lot of different latitudes, from the Singapore, which is practically at zero at the equator, and then all of the Japanese islands as you go up to Noto. So there's a huge range of exposures dependent upon the ambient UV. And he noticed that nuclear types dominate in Singapore. They weren't so common at much higher latitudes. Cortical cataract was common in the mid-latitudes, and it's this that we have some other evidence that there's a UVB or ultraviolet exposure rate. And things like posterior subcapsular was in Iceland. And certainly he reported, as did a lot of previous ophthalmic surveys, that cataract and presbyopia onset is at least, if not more, than 20 years earlier in tropical residents than compared to, say, the United Kingdom or northern Japan or someplace like that, or Boston in the US. Now, with regard to the lens, it's important to think about the anatomy and the fact that the cell nuclei of the lens fibers are around the equator, which of course is protected by the iris melanin when certainly this cross-section, this is of a 70-year-old male, so you see some yellowing here. But when the iris is constricted in bright sunlight, of course, the only area that's being heavily exposed is right along the visual axis. And so very little gets scattered back here to the critically important area of the DNA in the cell nuclei that are going to play a role in the generation of new lens cells. And so Venus Caronio, an ophthalmologist in Sydney, Australia, when he was younger, out of medical school, he had to serve some time out in the outback, and he noticed all these characteristics that it seemed like cortical cataract anyway always was starting right over in this area, where this, and that we're looking down in this view, and the nose would be here, blocking rays coming in this way. The iris blocks the rays coming in straight, and only the very oblique rays reach the critically important germinal layer of the lens. Now, what's amusing is that the epidemiologists, in trying to say, see whether sunlight exposure was playing a role in cataract, often came to the conclusion that there was no relationship with UV exposure, and their argument was they used a cohort of people who said they always wore sunglasses when they're outdoors, compared to people who said they never wear sunglasses. So they assumed that even poor sunglasses greatly attenuate UV, which is true. The filter does. What they ignored, though, was that most sunglasses traditionally have had no side protection. So what that actually does is that it may open the pupil a little bit and get more UV. And in fact, in the Beaver Dam study, they came up with a slight increase in cataract in women who always wore sunglasses, which of course they figured had to be irrelevant and didn't point it out. So actually they confirmed the hypothesis of Caronio that indeed there's a whole lot of a lot more cataract in the nasal quadrant. If we're talking about cortical cataract. What Sasapi's study also seemed to suggest that heat was more related, temperature was more related to nuclear ambient temperature over a lifetime, because the lens and the anterior segment of the eye is not core body temperature. It fluctuates up a degree or two over a lifetime. So someone who's living in the tropics has a lens temperature that's a couple degrees warmer than somebody who, say, lives in Europe or in the West. So in my studies of measuring ultraviolet in different environments and what the eye actually gets exposed to, it seems to always contradict what the assumptions of the epidemiologists have been, namely that the highest exposure actually occurs when the light overcasts, not for the skin, but for the eyes. And the lowest exposure to the eye is actually in high mountain valleys, where the assumption had been, oh, look, there's a whole lot more UV out there. Well, yes, there is, but it's not reaching the eye. And retinal exposure occurs in the superior retina, not the inferior retina, so I'll point out and mention. The key thing, the key takeaway, which should be obvious, is that ground reflection is really determining the exposure. We know that because when people are out late season skiing and they get snow blindness, that's the one time we see clinically significant photokeratitis. We don't see it in the summer when this UV falling on the earth is much higher. So we would assume today that cortical cataract has a strong association with UV exposure, and ambient temperature is probably the main etiological factor in terms of environment for cataract. Okay, so what's our natural protection when we're outdoors? I think a lot of people don't stop to think about the fact that besides the brow ridge blocking a little of the overhead, the major ocular shading really comes from the upper lid. And we did some experiments to try to check this out about what's really happening to the overhead UV that's coming from the sky when people are standing outside. And of course, we're all aware of the fact that when it's very bright, many people tend to be squinting. And so we try to measure this by measuring visual fields outdoors, at least vertical field of view. We had a survey of coal and we had a Christmas ornament. And we lowered that until somebody said that they could just see it. Whether they were looking downward or straight ahead, the lid stopped at about the same position. And the brighter the environment, the lower the lid. Such that, in very bright sunlight, a typical person will have about a 15-degree upper field of view in a not so bright sunlight condition, 30 degrees, and indoors here around 50 degrees. Most people have never paid any attention to this, but you can easily do it the next time you're in a dark environment and walk out in the sun. Just measure roughly where your upper field of view is, and then walk outside and you'll see that suddenly it's way down below. So our ocular exposure changes geometrically. This is some of the specific data from that study, and it looks like a huge variation, and it is a huge variation between the person who was least photosensitive to the person who was the most photosensitive. You can see that half the field of view, so like half the amount of UV and sunlight are getting in, this person compared to that person. Now, it looks like a huge spread all across here, but if you take the same person, this guy, this point, this point, this point, this point is the same person. So they all follow this sort of general average formula, but each person is a little different. And I was speculating with Jean-Marie that maybe there's something that could be usefully learned about visual function and retinal status and so forth, maybe retinal ganglion cell, by examining lid position relative to lumens. So what have traditional eye protectors look like? Well, we know the Inuit or the Eskimo used spatial filtering because they didn't have color filtered UV absorbing glass lenses to work with. So they used spatial filters, either a sealskin mask with 2 slits or at least a whalebone with 2 slits. And this greatly reduces the field of view. Well, it turns out that since UV is coming from the whole sky and reflected from the snow field, that attenuates the UV enormously. So that when we put this on our mannequin over snow, it was 10 times better than any commercial sunglasses. So we have to be careful not to be too arrogant about our space-age technology and our scientific method of assessing things. And if we go to other parts of the globe, desert nomads have not a sealskin mask, but a black cloth mask or head wraps and eye mascara things that work to limit the amount of UV hitting the eye. And in high mountain environments, in Nepal, in Europe, in the European Alps, in Chile, you'll find that original people all had brimmed hats. Now, why would brimmed hats be important? Because that heavy UV is only overhead, and they generally have grazing animals. They're not living on the very top of this mountain as a rule. And so green grass, it turns out, reflects less than 1% of UV. Snow is reflecting about 85%. And black asphalt is reflecting nearly 10 times as much as grass. So in built-up environments, we're getting a whole lot more UV if, say, you're a golfer. So the conclusion here about sunglasses is that we better have side protectors if we wear them, because if anything, this type of sunglass may actually increase the UV dose to the germinal flare of the lens. This guy has been mountain climbing, but he has leather side shields on the side. But you notice that he's he has heavy sun exposure, sun blister there, a very common spot for getting skin cancer. Before we leave the subject of sunglasses, I want to just mention polarizing sunglasses, because a lot of people ask, well, what good are they? Just because a sunglass is polarizing doesn't say much about how much UV protection is there, but the real value is in reducing reflective glare, because the sky is polarized. The bees and some insects with polarizing eyes, corneas can navigate based upon the sky's polarization. And Fresnel reflection off of water is heavily polarized. So when the sun is lower in the sky, you have a much stronger reflection. So we can summarize some of this environmental sunlight exposure to say that by just looking at cultural methods to avoid sun exposure, we can actually learn a lot. One question that keeps coming up is how much visible and UV gets to the retina. And of course, it's well known that as the eye ages, the shortwave cutoff moves further and further towards the longer wavelengths with age. And at infancy, the crystalline lens actually has a big window that extends down into the UVB. And this is the area that is particularly phototoxic. This area here is also phototoxic. So this has led to various speculation of the significance of all this. But Martin Mainster back in the 70s pointed out to cataract surgeons that the intraocular lenses that they were placing in the eye of elderly people had a big UV window. They would transmit a lot down here, and that was potentially a hazardous condition. So after that, they started adding some absorbers in crystalline lenses. The point that we should make is that this very small amount of UVB that reaches the retina, you wouldn't think that it would cause any effect that would be long-lasting. But we also know that malignant melanoma has a major correlation with excessive sunlight exposure in young children. That there's a strong correlation with, for light-skinned children, if they have a severe sunburn in youth, they may have a melanoma develop there many decades later. So since we're also talking about pigment cells in the RPE, who's to say that this little window of UV exposure couldn't be playing some radiological role? It's hard to say. There's no epidemiological evidence, but it's an area that probably should be looked at a little closer. And we should also point out that when you're in bright sunlight, only your upper hemisphere is getting significant exposure, but it's only getting reflections from the ground. So if we were trying to relate AMD to chronic light exposure, it would be important to be measuring what is being reflected, not what is overhead. So it may be that some of the efforts to measure UV exposure weren't really indicative for the retina, blue light or UV for that matter. So now let's turn a little bit towards ophthalmic instruments, which is another area of interest in the eye research program. And it turns out that the principal hazard that has been recognized with ophthalmic instrument is the intense light of operating microscopes during the cataract surgery. Now, normally we are not staring at a very bright light source like the sun when it is very phototoxic, when there's a lot of blue light and ultraviolet. When the sun sets, the atmospheric molecules have scattered all of the shortwave length UV and blue light, so that the color of the sun is not only yellow, it might even be orange or red. And if I use my little UV meter at this time and point it straight at the sun, I'll get no significant reading at all. But if I point it towards the zenith, that's where I would think something be, which of course is not anything high. So the changing atmospheric path lengths play a huge role in determining our exposure, showing how wavelength and geometry are constantly changing. And we can see this too for people who are fishermen or into water sports. When the sun is overhead, the reflection from the sun is only about 2%, but when the sun is lower, this might be 50% reflection, which is when, of course, polarizing lenses work very well. So, with regard to ophthalmic instruments then, we have several special conditions that we have to consider, because normally you have a natural aversion to bright light. You don't stare at a bright light source. But when you're undergoing an eye exam, you want to be cooperative as a patient, the ophthalmologist or oculist or optometrist, and you try to deal with it. Furthermore, the chin may be stabilized. You might be in a headrest. Pupils may be dilated. And during surgery, eye movements may be minimized as well. And of course, the aversion response is altered by anesthesia. So what we may not realize is when we have a very intense small source like the sun or a Welling arc or a laser or even an operating microscope, the light source itself is rather small. And one thing that mitigates that exposure is eye movements, involuntary saccades, which have been measured as a function of time. And this greatly lengthens the time that would be safe to stare at that source. But if you're in a chin rest or if you've got a contact lens on the patient, you now have a stable image on the retina. So the irradiance concentration of light on the retina can increase quite a bit. And of course, you don't have the aversion response. So there's a lot of experience with lasers, and of course we know retinal photocoagulators cause retinal thermal coagulations and things like that. There have been a lot of developments over the years, and of course in each case we have to look at what is the exposure to non-target tissues. And there are safety standards for ophthalmic instruments that take into account the UV, that's to protect against this, the near ultraviolet to protect against other problems, intense visible light, and then in the infrared. So there's about 7 different tests that have to be performed to make sure that if you have an ophthalmic light source that you've considered each of the possible effects. But this is what the patient sees when undergoing cataract surgery, and from an operating microscope. It's a brilliant thing that can be approaching the brightness of the sun if it's sitting on our planet. So it's very important that the surgeon not use the maximum setting on the output of the light if they don't really need it, or accept them. And here's an example of operating microscope burn. You can see the shape of the actual light source. And this is a graph that was prepared many decades ago, which is still fairly true, that the safety limits are approached or exceeded by a lot of ophthalmic instruments, but for the most part, except for very lengthy exposure, you don't run into the red, into an injurious situation. This is a summary of retinal irradiances or concentration of light at the retinal plane for different light sources, and visual displays and tablets and so forth are generally less than the brightness of outdoor daylight. And the typical retinal irradiance is around 10 to 30 microwatts per square centimeter on the retina when you're out in bright sunlight. And that's contrasted to the irradiance if you look directly at the sun, or a Welling arc is about nearly 1 million times higher than that. And here's the surprise to a lot of people. This is our little 1 milliwatt healing unit or laser pointer. that we might use in this setting. Why is a laser so hazardous? What is this unique aspect of the laser? Well, the physicists will tell you that it has to do with the brightness or the radiance of the laser. And this is not just the watts per square centimeter in the beam, but where it's coming from, what solid angle. So it's the watts per square centimeter per steradian, if you want to be fancy about it. By contrast with a conventional light source, even an arc lamp, if we try to focus the rays of an arc lamp, we get an image of the arc lamp over here. But with a laser, we'll get a nearly diffraction limited point that's only approximating the wavelength of that light, which is exquisitely small. Hence, you can have many kilowatts or megawatts per square centimeter focused on a tiny spot. And if you think about all the applications of lasers, they all depend on this physical characteristic of a laser, the radiance. That is, you have to have a tiny point focus of light to read the information off of a compact disc, or to weld steel, or to cut steel, or use in almost any clinical application of a laser. It's all because of the radiance you focus to a tiny spot. So even a 1 milliwatt laser is about 10 times brighter than the sun. And in any laser use in the eye, we have to take into account that we have very, very high radiances wherever we can focus that. And one useful development in safety of ophthalmic photocoagulators was the introduction of a fiber optic delivery system instead of the old articulated beam delivery system. I don't know if you see anybody old enough to remember that era, but there was a time when you could focus the photocoagulator down to a point and really cause damage. Whereas once it's been diffused by a fiber optic, it's a lot safer because you're imaging the tip of the fiber optic on the retina to produce that effect. So there are a lot of new types of diagnostic devices, and this is the one case where we can have Maxwellian view exposures with ophthalmic instruments. That is, a very, very bright source being focused inside the eye, either focusing in the anterior segment or vitreous or retina, depending upon what we're trying to do. So we've had to spend some time trying to understand exactly how hot does this little point get? Can we damage the lens even if we're illuminating a large part of the retina? And the radiance of the source in this case is very important. So there are a lot of newer anterior segment procedures that make use of lasers and bright lights and UV lights and so forth to either for diagnostic purposes or for surgical purposes, where we have to take into account these different potential hazards. Clinicians sometimes ask about photosensitization. This is a major issue for dermatologists, and it's not always recognized by ophthalmic clinicians. But the key thing to remember is that there are photosensitizing drugs. And some years ago, Bernie Hoppheimer at Hopkins at Wilmer did a phototoxicity study of fluorescein and found that it was photosensitizing. So you don't want to have a lot of excessive light exposure the first day after fluorescein exam, if you want to avoid that problem. And swirlings are another problem. Patients who are being treated with near ultraviolet and swirlings for treating psoriasis and things like that, they have to be given eye protective goggles to wear for the first day or two until that photosensitizing drug has been eliminated through their system. There's a phenomenon of vision that is common in cataract patients after surgery, and that is erythropsia, and that's generally indicative of a lot of short wavelength light and ultraviolet getting back to the retina. There was a vision scientists in the Netherlands back 50 years ago did a study of how the color vision is affected if you have UV getting back to the retina. And Louise Sloan at Wilmer used to always tell her students that one should give cataract patients scalar lenses because of this problem, because if they reduce their color contrast and everything else. That was before the development of IOLs for that filtration. So I have a few more items that I can go to. Let me just go, since we've got a couple minutes, let me go ahead and just mention a couple of other potentially related subjects, and that is the fairly recently discovered, only 12, 15 years ago, the intrinsically photosensitive retinal ganglion receptors that have a photosensitizing opsin in them, and these actually respond very slowly to the ambient light and clearly play a role in determining pupil size and lid closure and everything else, and maintaining pupil size. So it may well be that one could develop some clinical diagnostic tools for some patients, like photosensitive patients, by looking at this particular receptor. It has a peak somewhere around 407 nanometers, which is down in the blue. And another point to be made, of course, is that the cone concentration, of course, is very strong in fovea. The relative intensity of light on the retina looks something like this, and then rod concentration out like this. And then the ganglion cells are out around in this area, at least the ones that people generally pay attention to. So there are a large number of patients that are exposed to bright light in the morning to treat psychiatric depression, so-called seasonal affective disorder. And it's quite clear that this process worked, and it's clearly resetting the circadian clock, and also in treating the concentration of, let's see, melatonin in the whole cardiovascular system, which of course is a neuroendocrine controller of a lot of functions in the body, different organs. Different types of lamps pose different risks, and this just summarizes the fact that the worst case conventional lamp is a xenon arc lamp, and probably the safest is the good old 60-watt frost incandescent lamp, which is now been outlawed in most countries anyway, and is being replaced by a lot of LEDs, which actually have a lot of blue light, so they start to move up in this area. And one other thing, since you're interested in ophthalmic devices, there are a lot of infrared, not UV or visible, eye trackers that are used in many different applications, but one interesting application is communication by gaze interaction. And this is where people with ALA or severely handicapped and have lost most of their muscular control still have some muscle control. The last things that goes are the eyelids and the facial muscles. And so they can use those to control with their gaze, a computer mouse and so forth in a wheelchair and get about do things. So there's an example of infrared exposure, but infrared is vastly less phototoxic. If there's any effect, it's a thermal effect, and these things are very safe. Okay, so we can go back to questions. I guess you had a question. not documented injury. It's getting up there, and if you make some laboratory measurements of them, they look very dangerous. But because, you have to hold your head and everything steady and so forth, it's not going to be a very lengthy exposure. So wavelength is important, but time is also. So if the exposure is fairly short, it's not a problem. For example, when we have retinal injuries from operating microscopes, it's because something went wrong in the surgery and it was an extraordinary way, say 15 minutes before you get into trouble. Okay. If you have some, yes.
So I'm curious about, to think about using light for stimulating blind retinas, for photoreceptor damaged retinas, so that they have good ganglion cells. Could you think it is a suitable range of energy that generates some phosphines and without killing the cells?
Well, I can only say that those would be pretty high light levels. There are, some of the retinal implants make use of a light, like a laser that scans and puts an image on the electrodes in a retinal implant. That's a anchor type of implant. I'm not sure if I've heard that idea before, but the phosphines, are certainly react from pressure. So if you've had a pulsing laser source, you might be able to get some specialized stimulation. I think I've heard of something along that line before, but as far as I know, nobody's really played around with it. But since phosphines are excited by mechanical force, I could well imagine that you could get down to a low level of thermal expansion in the retina if you were stimulus, and if you put it spatially scanning and then zap things to create a pattern, I guess you might be able to. An interesting aside on this is that your ears, of course, are incredibly sensitive, and you can actually hear a radar that's pulsing because of thermal expansion in the eardrum. And just the radar, at levels that are quite safe. So maybe there's a possibility there. At least that's the way I would think of pulsing.
You would use an infrared source
Yeah.
first?
Well, you certainly stay away from the UV because you can damage tissue, and so, I'm told that various types of retinal diseases, there's might be some sensitivity, just having an amplification of light on the retina might be okay, but I'd certainly try to keep down towards the red end of the spectrum to get away from phototoxic complications.
You come up with something?
So I want to talk about numbers.
I have a non-scientific question, especially here in Miami. For instance, on Key Biscayne, mother and father are wearing fashion sunglasses, and the baby in a carriage, no sunglasses at all. Do you think there's enough public health education regarding protecting children's eyes?
Yeah, and I know, for example, when ophthalmologists in Israel had a big campaign for that sort of thing. The problem is that babies tend to knock things off. Little kids lose their sunglasses very quickly. And I would say if you're going to have eye protection, you want to have it more in goggle fashion or visor fashion. And I think I would, being a grandpa, if I still had a toddler or infant, I would look into something like a sun shield, and I think I've seen those. Australia has had an epidemic of skin cancer over the years, so they have a huge public health campaign down there on skin protection, and they also talk about eye protection and little hoods and things like that. But I don't think it's, I don't think I would just scale the size of sunglasses down to a little eye. That'd probably be more of a problem than that.
Just to add to that, I had done an experiment on mice using just regular fluorescent light in the room for exposure, and basically just by exposing the mice at different age from infancy to old age for 24 hours to white fluorescent light, we could see retinal photoreceptor degeneration in really early young age. But as retina matures, then that damage stops. However, as the retina gets older, then the damage starts again. So I am not aware of whether there's similar response to such phototoxicity in human, but I think if we could extrapolate and try to infer the results from the animal study to human, I would definitely want to advocate for some protection at an early age, definitely when the retina is still at risk for injury.
That's a very good point. The repair mechanism, cellular repair, is greatly diminished as you get older. So I'm sure that applies to the human eye as well. It's very well recognized in skin that it's terribly important in skin cancer patients to get them to just stop sun exposures. They really have to use good sunblocks and so forth. Where compliance is so bad is when on an overcast day, people think they're not getting any significant sunlight exposure, it can be chilling even. But that's when the dermatologists see the real severe cases of sunburn, because you see, water blocks the infrared, so you don't feel so much heat, but it just scatters the UV and redistributes it as far as the eye goes, maybe actually more exposure. And that's normally when people don't wear sunglasses anyway. Yes?
You mentioned in one of the slides that, I guess, central cataracts have more to do with anything temperature than
Yeah, nuclear cataract seems to be related to temperature. You think of the fact that there's not a lot of metabolic activity in the nucleus. And so it's just been speculated that you have sort of solar degradation of those molecules. But the epidemiological studies and most laboratory studies don't really support that. But ambient temperature seems to be pretty well related. There was actually the chief of ophthalmology at the University of San Juan in Puerto Rico back in the 60s was practically crusading on the argument that heat was the bad thing, not ultraviolet. And of course, the photochemists and the photobiologists who were studying UV effect thought the guy was crazy. But what he pointed out, clinically, he saw cataract at a much earlier age, down, say, for example, along the seacoast in Latin American countries where he went. But if you went up the mountains, he didn't see the cataract until much, much later. So he argued, look, they're getting quite a bit of UV up there. Now, what my measurements say is they actually get less UV in the eye, but still there's a strong temperature correlate there. And the geometrical factor of the UV coming in from the side fits so well with Coronio's hypothesis of the cortical cataracts, folks starting all over.
What's the mechanism behind that? into it behind temperature causing the
Oh, it slows down the metabolic rate. So you can think of it as accelerating the aging of your biological tissue if you live in a hot environment. It's, we normally think of thermal effects having a threshold. And for coagulation and things like that, that's pretty accurate. But if you have the same molecules there over decades, and they're not being constantly replicated as they are in the skin, then the thermochemistry theory says that you're going to increase all the metabolic processes and age that tissue over the lifetime. But the photochemists don't normally think in terms of thermal effects. That's a different crowd of chemists, biologists. And so, and they don't talk to each other.
Any more questions? Please feel free. Anyway, David is not very far. He has a little place in, where is it in Florida? Right. So if we need him, he will come down to it.
At least in the winter time, of course.
Thank you, David.